Okay, so let's. Okay. Right. So let me start. So okay. So where is the screen? Yeah. So yeah. So it is equivariant K theory. Right. So I don't know how should I start this. So I am supposed to give. Huh? What is this? What is that?
You have an issue?
Yeah, I think this was getting my. Yeah, now it's fine. So yeah, so it's an introduction to equivariant K theory. So I don't know where to start, but let me start from somewhere. So let me first. Okay, so remember that equivariant K theory can mean algebraic and as well as topological, or yeah. So, but this will be basically algebraic, algebraic equivariant K theory. Right. So let's. What is the setup? Setup is that let's start with. Well, you can define very generally, but okay, let's start with a very general thing. So I hope that people are familiar with some algebraic geometry here. So now let's suppose that you have S A. Let's say S is an affine scheme. Let's say some spec of some commutative ring. And let's take G, a group scheme over S. Right. So group scheme is just like some algebraic group, so that the fiber wise for every fiber is some group. And okay, so there is a formal definition of that, which let me not get into. But it's just some generalization of algebraic groups, right? And let's suppose that X is an S scheme, which I read usually at S scheme over S. So what's the meaning of saying that G is acting on X? So GXN on X. So GXN on X. So what's the meaning of that? It's basically the meaning is exactly what you expect, that G is acting on this topological space. But this action has to have some algebraic properties, so you define in some more formal way. So the more formal way to define this is that you have some, you have this product. This is all over S to X. This is the what is called the product operation, the action operation. So such that if you take element G and some X, then mu of G comma X is exactly G acting on that point X. But you have to be very careful here, because this is a very general algebraic geometric fiber product over a scheme. So it's this fiber product is not product wise. Every element is not of the point, not of the type something here, something here. So you have to be very careful here. So that's why I'm not writing like that. So yeah, so you have this is a morphism of algebraic schemes over S, and it satisfies certain gluing condition, or whatever, certain, like let's say cocycle condition. So what it means is the following. So you have this G cross X, everything is over S, and then you have this identity cross mu. This goes to G cross X, right? And then here you have mu, Let's write, yeah, mu x, sometimes we write x. On the other hand, here you have this map to G cross X. Now here, this is G cross G to G, this is a multiplication map, right? Because it's a group scheme, so you have the multiplication operation. And then here, times identity of X. So you have identity here. And then here you have this mu again. And we say that this diagram commutes. So basically, this is commutative square is simply saying that if you have two elements, G and G prime in G, the pointwise, and if you multiply G with X, and then you multiply G prime with GX, it's same as you multiply G and G prime in the group G, and then let it act on X. That's what it means basically. It's exactly, it's a kind of geometric formalization of what you know in topology. It's a kind of algebraic geometric formulation of what one knows in topology already. Right. So this is the meaning, and if this happens, then we say that X is a G scheme. And we also write sometimes like X scheme. My notation will be S over G. Yeah. So in general, we will we will mostly we will be interested in the case where S is a spec of some field K. And in that case, G is an algebraic group over K. And remember that an algebraic group by definition can be abelian variety also, right? And semi-abelian variety also. But whenever we study equivariant geometry, we usually assume that G is affine always. So for us, an algebraic group is always an affine algebraic group. Right, and we say that G is linear. It's a linear algebraic group, which means that there is a closed embedding of G into some GLN over K, or some n. Right. In that case, we say that G is linear because for obvious reason, because it's a closed subgroup of a linear group. Right. So this is the elementary stuff. And now, what do you want to say? So now we want to say that what's the meaning of? So now let's start. We suppose you have this X is a G scheme, which means that X is a S scheme, which is equipped with GXN. And suppose you have F, a coherent sheaf, which I usually write this category of coherent sheaf like that. So when do we say that F is G equivariant? So we say that F is G equivariant if it just basically means that G acts on F, and this action of G on F is compatible with the action of G on X. But again, more formally, we write like this. It means that, well, what? That there exists one resist an iso. Let's call it, what do I call it? Let's call it theta of F from mu star of F to P to star. So what is P2 here? P2 is the second projection from G cross X to X. So remember, F is a sheaf here, so you can pull back by P2, you can pull back by mu, and the thing is that there's an isomorphism. Right. And such that to this isomorphism, theta F satisfies some co-cycle condition. Right. So basically, what does the co-cycle condition actually means? It basically it's not. It's kind of a little bit complicated to write, but it's this is one. Yeah. Right. So what it means is that basically, I will not write this. It just means that that this action of G on F is satisfied some associativity condition and those stuff. That's what basically this cocycle condition means. So this cocycle condition on F is very similar to this cocycle condition here, right? So because to explicitly write down this diagram, I have to explain various terms and why it makes sense. So it will, I don't want to get into that right now. Right. So in that case, we say that F is the equivariant sieve. Actually, this you can define for any sieve of abelian group on X. It did not be coherent or quasi-coherent. This definition makes sense for any sieve in Zariski topology, right? So then we write like this. So we write Gx. So you have various category, right? Quasi-coherent Gx. You can take locally free sieve, which you write like this on X, and so on. So you have this inclusion, right? And then, of course, this sits inside all sieves, equivariant sieves on X of abelian. So this is the category of quasi-coherent sieves which are G equivariant. This is coherent sieves are G equivariant. This is locally free sieves which are G equivariant. Right. So, so it's clear, right, that if you forget the Gx, and then each one of these category embeds inside the corresponding category. In particular, you have this, which we are mostly interested in. This clearly embeds inside all coherency, right? So, but you should notice that. So similarly, if you take all vector bundle, a G equivariant vector bundles, G equivariant vector bundles means G equivariant locally free, and this sits inside all vector bundles on X. And the point to notice is that these vertical inclusions, they are actually fully faithful, but the horizontal inclusions are not fully faithful. They are fully faithful. They are faithful, but not full, because as you see that if you take two coherent sieves with equivariant, then you may have a morphism between them, which is not preserving G equivariance. So these horizontal maps are not actually full embeddings, but vertical maps are. So remember that if F and G are two quasi-coherent sieves and you have some map F, then we say that this map is G equivariant or G equivariant map if you have this, right? You have this mu star of F. Remember, we have this theta of F to P2 star of F. Then here you have P2 star of G. This is P2 star of F, and this is here mu star of G. This is mu star of F, and this is theta of G, and this diagram commutes. If this happens, then we say that F is also G equivariant, which means that F preserves G action. So what I was saying that you may have a two G equivariant sieves, but a morphism F which does not satisfy this condition. It can happen, right? So this you have to keep in mind. So we will be mostly interested in this diagram. Right. So now that we have this, so now let's take this category coherent G equivariant coherent sieve, as you can see that this is an abelian category. Right, very clear. And if you take G equivariant locally free sieves, then this is not an abelian category, but it's an exact category, which means that it is a full subcategory of an abelian category, which is closed under all extensions and exact sequences. For example, if you take locally free sieve sitting inside all coherent sieves, then this is not abelian, of course, because a kernel or co-kernel of a map of, well, if you take a co-kernel particularly of a map of locally free sieves, then it may not be locally free in general, but it is clearly an exact category. Right. So once you have this exact category, now we can go to Quillen. So Quillen says that whenever you have an exact category, you can define its K theory. Well, how do you do this? So if you now you recall, so now this has nothing to do with G equivariance. If you take any exact category, given any exact category, let's say C, what you do is, well, if you recall that you Quillen main trick of Quillen is that what is the most famous technique of Quillen that he call it the Q construction. So if you have an exact category, then from that you can define a new category, which Quillen taught us how to do is called the Q of C, where the morphisms are not all objects are same as C, but the morphisms are slightly different. So morphisms are something like, well, if you have A and B, then what is the morphism? So morphism means it's a diagram, zigzag diagram, like you have some C and you have some kind of, this is called admissible epimorphism, and this is called admissible monomorphisms. There is some diagram like that. So right, so this kind of diagram, the zigzag diagram, is a one morphism in Q of C's. And then once you have this Q of C, then you can define its nerve, right? So you can define its nerve. So if you have any category, you can define a nerve of this category. So basically, here objects are the finite sequences of objects in this category with composable maps, and morphisms are this component-wise morphisms that the diagram commutes. And then once you define the nerve, then it becomes a simplicial category, and so you can take its classifying space. Right. So usually people don't write this nerve. We just write this as B Q of C. So now this becomes a basically some kind of you can think of some simplicial set, and you can take its geometric realization, which is called the classifying space of this category, and then you take its group completion, the loop space. So loop space, if you remember that there is a functor from all topological. If you don't do the group completion, then you can easily see that this is a topological monoid because you are taking the exact category. So it's a topological monoid. So once you have a monoid in any category, then you have the functor of group completion, which is the left adjoint to the inclusion of group objects into the monoid objects. So this is called the group completion. And in topology, sometimes people also say the loop space of this topological monoid B, Q, and C, B, Q of C. Right. And then now that once we have, then if you have this category C, you can define Q of C as exactly this. Sometimes, actually, it turns out that actually this guy, this is an important fact, that this guy, once you take this group completion, then it becomes an infinite loop space. So what is the meaning of infinite loop space? That means that it's basically if you take any n, then there is some some topological space you can find out, so that it's nth loop space is this guy. So this is nth loop space of everything. So, but once you have an infinite loop space, if you recall your topology, then you can define something called the S spectrum, right? S1 spectrum. Because it's a loop space, so you can take some sequence A1, A2, AN. So that A1 is clearly the loop space of A2, A2 is loop space of A3, and so on, right? Because it's an infinite loop space. So from this, actually, you get an S1 spectrum. And that is what I call this K of C. So K of C finally is actually an S1 spectrum. It's even better than that. Remember, an S1 spectrum maybe any sequence of simplicial set such that say AN such that there is a map from AN to suspension of AN plus 1 and so on. But remember, the suspension and loop space are adjoined to each other, so an infinite loop space is clearly S1 spectrum is better than that. So right, so we have this. So now that we have, then we can define its homotopy K theory of this exact category as the higher stable homotopy groups of this is infinite loop space K of C. Right? So now that once we have this tool, so I can define the equivariant K theory of X as this simplicial spectrum K of omega of, well, what I'm doing here. I'm writing some. So basically, this is just K of coherent G of X. No, I made a mistake actually. I should be careful here. Well, so let me don't write this. I don't know what notation to use. Let me write this as G of G. The bad notation, but I am sorry about this. So K G of X is basically K of vector bundle on X. So sometimes I also write that K of B of G of X. So clearly, this gives you a commutative diagram of S1 spectra. K G of X, K of X is a forgetful map, and this is GG of X, and this is G of X. So this is the basic diagram one studies in equivariant K theory. So we define equivariant K groups. I can take the homotopy group, then you can get this kind of GGI of X. Remember that because these are infinite loop spaces, so basically they have no negative K group, homotopy groups. So they have like so, but that's not good. So actually, you can define negative equivariant K groups also, and yeah, so that is called the Bas construction. Roughly speaking, Bas construction, what it says is that suppose you are over some scheme S, then you have this map, right? K of kg of x t, where t is a variable, cross kg of x t inverse. And then you have kg of x t plus minus 1, and call this map theta and take the co-fiber of this, let's say, whatever it is, the co-fiber. So if I take here ki k0, let's say k0, then this guy will be exactly, let's say, you can define it, roughly speaking, k minus 1 of x. And you keep going. So this is one way of defining negative k groups, equivariant k groups. Same thing happens for the ordinary k groups also. And it turns out that these groups may not be zero in general, which is saying that this map may not be surjective. Right. So we have this now equivariant K theory, and we have equivariant G theory. Right. G theory is equivariant coherency, and this is K theory equivariant vector bundles. Right. So what else? So we have this now. Mm, so now let's see some examples. So let's take x equal to just point itself. Point means equal to s take k. Then what is this k naught of g of k? Well, you can see that this is nothing but the representation ring of G. Well, I should tell you that this Quillen already proved that if you have an exact category like this, and if you take pi, like the first pi one, yeah, but yeah, right. So then, without taking the loop space, then remember that. So in particular, if you take the pi naught of that, so it's k naught of g of point, or k naught of g of x, you can check that this is nothing but the three abelian group on isomorphism classes of G vector bundles modulo short exact sequences. As usual, we do in right. So, but if you do this, then it is very clear that k G of space k is the representation. Right? This follows and this fact that this is equal to this very strongly uses the co-cycle condition of equivariant shifts. So co-cycle conditions are very useful. If you don't use the co-cycle condition, then you cannot prove this equality. Right? Because then you are saying nothing in this case. So, in other words, what I'm saying that in the definition of equivariant shifts, if you recall, there were condition 1, condition 2, if you just prove this equality. So, co-cycle condition we have to, you should not forget. That's what I'm trying to emphasize. It's very useful in calculation. Right. So, right. So, why it is a ring? So, it is a ring under the tensor product. In general, if you take any G scheme X, then K naught of G of X is a commutative ring, and any Ki G of X is a K naught G X module. Right. So what is the advantage of this? The advantage of this is that it is very useful fact in equivariant K theory. Why? Because and this fact actually it's a deep fact, but it's very difficult to explain right now. But this is the isomorphism actually which allows you to study equivariant K theory, and sometimes actually this makes equivariant K theory a lot easier than ordinary K theory. It's surprising fact. Why? Because of this fact, and you remember this is representation theory, right? You are studying representation of the group. So in equivariant K theory, you can use all algebraic geometry as well as representation theory, which you cannot in ordinary K theory. There is nothing, no representation theory there. So the using the representation theory, it has lots of tools actually. That's the beauty of representation theory. It has lots of tools. So you can use those tools to compute equivariant K theory. And that's why equivariant K theory is interesting and often easier to compute because you can use representation theory. Right. So now what else? Right. So and then in general, if you take any X scheme, then if you take this K I G of X, then this is an RG module. Clearly, right? Okay. So for every I. Right. So now, what do you want to do? What next? Yeah, and you see, if you recall that this RG module, this RG, this ring, is what is this ring? This is just the free abelian group. The irreducible representations of G. In particular, this ring is always torsion free. Okay, that is free. Right. And this is not very hard to prove that this is just free abelian group of irreducible representations. Yeah, and what else? Saying that RG is equal to free abelian group, this is also some kind of, you can think of this as some kind of Jordan-Holder theorem. Right, and so let's see, for example, G is equal to some split torus. Of rank n. A split torus means if your field K is not algebraically closed, then not every torus is of the form some GM cross GM cross GM for some n. It may become a split after some finite extension, but it may not be a split always. So suppose you take this G to be a split torus, then what is RG? Well, this is not very easy, very difficult to prove because we know that all irreducible representations of T are one-dimensional and given by G representation of GM is given by some lambda x going to lambda to the power m times x, where lambda is in GM and x is in GA. So using that, you can show that this guy is nothing but G T1 plus minus 1 Tn plus minus 1. Yeah. And if you take any reductive group, say G is connected, let's say a split reductive, not connected, sorry, what I'm saying. Leave that properly. So G is a split reductive. Yeah, the system is connected also. So then, so it has a maximal torus, a split maximal torus T, and then you have this RG, and you clearly restrict to RT, right? And what is the relation? Relation is that actually this is equal to RT and the inverse. This is the while, W is the while group. So this is an isomorphism. So this is not very hard to prove. So in particular, for example, if you take G equal to GLN, then we know that the while group is a symmetric group on n letters, and then so basically once you take the T1, T2, Tn and take the while group invariants, then you just take the symmetric polynomials, and that will give you the representation ring of GLN. So which we are going to use, which is very useful. Right. So what else? Yeah. So in general, if you take this R of G and you take K, what is K of G? This is the coordinate ring of, remember G is affine, so it has a coordinate ring. Right. What is the relation between RG and KG? Well, first of all, they can never be same, right? Because RG is over Z and this is over K. It's a Z algebra, Z algebra, it's a K algebra. Nonetheless, you have a map. Right. What is this map? Basically, the map, you take any representation, let's say, what do I write here? Representation V and rho. Then you just take the character of rho. Right? And as you see that this character, since character is always like some kind of abelian, it's a one-dimensional thing, it maps to GM, so which shows that, and as you see that this character clearly gives you a regular function on G, right? But since G is affine, a regular function, and since V is rational, it's a rational regular function on G. But any regular function on G is exactly the coordinate ring of G, right? So you get this map. This is just called the character map. And as you see that because character is a one-dimensional character, it's a one-dimensional representation in this to speak. So it is always abelian, right? So that means that it will always factor through. Now G acts on this Kg, right, by inner automorphism, and this always lands inside the invariant under the action of G by this inner automorphism, right? So basically, what is this guy here? This guy, if you see, this is nothing but, if you know this thing, just a class function on G, right? Under the inner automorphism of G. So basically, and the fact is that you can show that this map here is injective. And here is a fact that if G is reductive, then this is iso. Remember that a linear algebraic group is reductive if unipotent radical is the torus. Right. So, and this is not very hard to prove. I have made a mistake. Obviously, this is false. How is this can be true? So I should write here, you take this guy, tensor over Z with K. Then otherwise, it's never going to happen, right? I say because it's a Z algebra, it's a K algebra. If you do this, then this is an isomorphism. So this tells you that the coordinate ring of a reductive group basically is very closely related to the Riesz representation ring itself. Right. So all these facts are very useful when you are studying equivariant K theory. Now what else? Yes. So right now, let me give you some more examples. So two interesting cases, two cases of interest. So the first is, let's suppose that G acts trivially on X. So now X is a K scheme, K is a field, and G is an algebraic group, it's a linear algebraic group, let's say. And G is acting, and this action is trivial. Right. So you expect this to be something very simple. So, and it is indeed simple. Why? Well, let's see. So, what is the meaning of G is acting trivially? It simply means that you remember that we have this map G cross X to X. One is the multiplication group action map, and one is the projection map. So this condition is saying nothing. First condition in the using cocycle condition. Actually, you can see what? You can see the following, that if you take all coherent sheaves on X, right? And you take some representation of G, and you take the tensor product, then you get this thing here, right? It clearly becomes G equivariant sheaf because G is acting trivially here. So you have this puncture. Now, because you are dealing with exact category, there is a way of you can think of this in the, if you do in the more like categorical thing, like you can think of this as some kind of infinity ring spectrum and blah blah and so on and so forth, or a stable infinity category. If you go in this language, so instead of getting into details, I can just tell you that you can define something called X, and you can define something called a snash product with respect to representations of G, and then you get this. Right. And this tells you that you now, if you use Quillen's K theory, its localizations and various theorems of Quillen theorem A, theorem B, blah blah, if you combine, then what it gives you is the following. It gives you that if you take G of X tensor Z R of G to G of X, and this is a weak equivalence. Right. So this is very simple. So now you see the equivariant K theory becomes very, very simple. It basically it's nothing but ordinary G theory of X and tensor with the representation being of G. Yeah. So, and there are various ways to prove this. One way is that you can prove using some localization sequence, because the map clearly exists. To prove isomorphism, one way to get a quick proof is that you use some genetic slice theorem. So that anyway, you can assume that it's fine, and then genetic slice plan you can reduce to case of torus, and torus is very easy to show, and blah blah blah. So let me not get into this, but it's not difficult to prove if you know some K theory and some, yeah, basically K theory and plus some SGA kind of thing about how does uh, an algebra with torus section look like, and so on. Right. So you see that the trivial action case, the equivariant K theory, nothing but the ordinary K theory. Now, second case is when Gx is opposite to trivial action freely. This is completely opposite to trivial action. So what does that mean? Freely action everybody knows, but let me recall for you that in algebraic geometry there are many notions of free action. So you have this map, right? Call this map psi. What is this map? Take G, X, map it to Gx, comma X. And we say that this Xn is free if some people say, for example, if you look at GIT, Mumford says that Gxn is free and this is a closed immersion. Some people say it's just an immersion. Some people say just a monomorphism. So let me just take it as a closed immersion. Remember, in topology, you will say this is free if this is a monomorphism, right? But in algebraic geometry, monomorphism and epimorphism are bad objects. You have to say some categorical thing, either an immersion or closed immersion. Let's say it's a closed immersion. Right. And as you see that it means that, and suppose that means that there are no stabilizers. And suppose that the quotient x to x mod g exists. This may not always exist, okay? Even if the xn is free, call it phi. But this is always an algebraic space if you know some algebraic geometry, but it may not be a scheme. But in very often this is a scheme. In fact, if this is quasi-projective, this is also quasi-projective. And GIT gives you a condition when this is a sort of a quasi-projective scheme. Let's assume that is a scheme exists, the quotient exists, call this equal to y. Then it turns out that you have this map, right? Coherent sheaf on y to G equivariant coherent sheaf on y, x. Similarly, vector bundle on y to G equivariant vector bundle on x. And the point is that these are equivalence of categories. And how do you prove this? This is what we call the theory of effective descent in algebraic geometry. Just the descent theorem. Right. So again, what happens is that in particular, what you get is that kg of x is nothing but ordinary k theory of y, and gg of x is just the ordinary g theory of y. So in this case also, there is no equivariant thing is not there is no equivariant basically. Everything becomes ordinary k theory, ordinary g theory. So this case is also very interesting, and often you reduce to this case or the trivial case. So why these cases are interesting? It's not just for the sake of telling you these two cases, but the point is that in most of the cases, when you are trying to prove some theorems, you always try to reduce to these two cases because these two cases allow you to go back to your ordinary K theory. That's why it's very important to understand these two cases and some variant of this. Right, may not be exactly you may get into these two cases, but something very close, but that is very difficult to tell at this moment. Right. So now, what do I want to say? What else? So now, some properties, some formal. Of equivariant K theory. So, well, these are some obvious things. So, first is that suppose F is a map of G equivariant map. Then, okay, so let's say, let's erase this first here. So, first here, then exists pullback f upper star from kg of y, kg of x. So when I don't write ki, I'm just writing a map of a spectra, okay? And then you can take the homotopy groups and get map on k groups. 2, there exists a fullback gg of y to gg of x if this is not always true, if f is flat. Right. And then 3, yeah. So here, right? 3 that there exists f lower star from gg of x to gg of y if f is proper. 4, there exists f lower star from kg of x to kg of y if f has finite two dimension. So I did not define the notion of finite two dimension, but you can look up in some book. Very very easy to define. It just means that f lower star of Ox as an OY module has finite two dimension. That means there is some IN such that the total of that with respect to any OI module becomes 0 for all I bigger than or equal to n. Right. And furthermore, if you have this commutative diagram, let's say x prime, y prime, y, x, this is my f, this is my f prime, this is my g, this is my g prime, and suppose this square is transverse. Suppose this square is totally independent. Totally independent means as an OI module that the total of OY prime and OX is 0 over OI. Totally independent and it's Cartesian, of course. This is such a square is called over the transverse square. Then you take this f and assume that and let's assume that g is proper. Right, then you have this f upper star proper and of course proper and finite two dimension. This is G prime. Then you have this map. This is equal to, the theorem is that this is equal to G lower star composite F prime star. Right, so and the proof is very basically exactly same as what you do in the non-equivariant K theory. Nothing different. And next is the localization. So suppose you have a G invariant open subset X and with complement Z. This is G invariant. Then there exists an exact sequence, log exact sequence. Okay, so let me do the following. Let me not write like this is a bad thing to write. There exists a homotopy fiber sequence GG of Z push forward GG of X J upper star GG of U. Right. However, you have to be careful here. Careful about what? This kind of exact sequence does not hold for K theory. Remember, I am writing G here. So, for example, if you write here Kg of X, then this you write Kg of U. And what is the co-fiber? Co-fiber is something else. It's called, usually people write GGZ of X. So what is this? This is the K theory of category of K theory of category of equivariant perfect complexes on X which are acyclic on U. So remember, a perfect complex is basically is a complex of you can take a bonded complex also, or you can see it's cohomologically bonded anyway. It's a cohomologically bonded complex of equivariant coherent sieves, such that it's locally they are like locally they are quasi isomorphic to bonded complexes of locally pre-sieves. So we say then you say that it's a perfect complex. So the point is that then this is and it clearly maps to this, and point is that this is also a homotopy fiber sequence. So this is EG. This is exactly like in Killian, but this is not so easy. Yeah. Right. So this allows you to do a lot of computation. Now here you see that again here if you write, let's say, k naught of x to k naught of u, right? Okay. Then this map may not be surjective, right? Because it's not true that uh, if in particular if x is singular, then if you don't have negative k theory, then where do you go here? And that's why it is important to define negative k theory, and then it keeps going in the negative direction forever. So that's the advantage of defining negative K theory, which allows you to continue the long exact sequence in the negative direction, because it's not true that if you have an open inversion which is G invariant, then the K naught of X, K naught G of X to K naught G of U is rejected, which is always true for coherency, but not for vector bundles. Right. In other words, if you have a vector bundle on open subset, it doesn't extend always to an equivariant vector bundle on the whole scheme. That's why you require negative K theory to measure the difference, measure the obstruction to extension of an equivariant vector bundle from an open subset to all of X. You need some numerical invariant, numerical invariant measures that, and that is exactly what K minus 1 does. Right. Now, let me do some more serious stuff. Further, more interesting thing is about equivariant K theory. So, next is the following. Okay, so now, where I am. Where is this? So again, a problem with my this writing thing is just, yeah. So now it's again back. So now assume G is a split reductive. Okay. With maximal, and T is a maximal torus. Right. Then what we can do? So now you notice that this isn't true in general. You don't need. Suppose you have in general. Suppose you have H is a closed subgroup of G. Then you have this map, right? This is what do I write here? G of X tensor R over RG RH to GH of X. Right? Right. The question is, when is this an isomorphism? If you know this, then things becomes a lot easier, right? Then it tells you that if you know the equivariant K theory for G, then you know for equivariant K theory for every closed subgroup of G, just by base chain. So you don't expect this to be an isomorphism always, right? However, what is true is the following. I think with some mild condition. What is true is the following. With some mild condition. So what we can do is, well, let's see the following. Let's write here g of x, right? And let's write here, what do we write? Take the smash product over, let's write here g of point. And then here you take gh of point. This also maps to g of x. And the point is that this is a weak equivalence of a spectra. S1 spectrum. So in particular, if you know some homotopy theory, then this actually implies that there exists a spectral sequence, namely E2PQ equal to Tor GG KG here, KG point P of KG KH point, and then here you have G Q of X to uh, G P plus Q GH. Actually, I should tell you that you can define this. You can simply write here RG. You can simply write here RG. With some mild condition, and this is the best you can expect actually, that this happens. So yeah, these theorems are not trivial. They are some very non-trivial theorems. So let's say a special case. So here now G is reductive and T maximum to S. Then actually what happens is that this spectral sequence splits. Well, again with some mild condition, namely that the what you know is what we should say that the commutator subgroup of G, what you call simply connected. So, for example, if you take GLN and SLN and so on, then this is okay. What I'm saying is spectral sequence split. What I'm saying nonsense to say that degenerates. So in particular, you get this iso G I of X tensor RG to RT. This is isomorphic to GT I of X every. And this is great. right? Because it tells you that if you want to compute equivariant K theory for Txn, then you simply take equivariant K theory for Gxn and base change to the representation ring of T. Right? So it really allows you to compute. If you know one, then you can compute other. In fact, you can say that you can say the following. In fact, there is a very close relation, namely that you write here Gg of x, and then you have the restriction map, right, to Gt of x. Restriction map, right? Basically, where is here. And remember, by this theorem, what is this? By that theorem, this is a corollary actually, I should say, corollary of that. A very interesting corollary. This theorem says that again I will do is here, right? G of x cancel Rg. But now you can do, I will tell you later, is something called Morita isomorphism. So this is same as Gg of x tensor Rg, and this is Gg of G mod T. So you see that the point is that Morita isomorphism tells you that if you have any closed subgroup, then its representation change is same as the K naught G of R mod H, G mod H. I will come back to this later. So nonetheless, let's assume this. Right. But from here, you can go to further to Gg of x tensor Rg to Gg of G mod B, where B is the Borel subgroup. Why? Because G mod B maps, G mod T maps to G mod B. And the point is that the equivariant K theory are same because what is Borel? Borel is this maximal torus plus the unipotent radical. But we know that for unipotent radical, any unipotent group, in fact, it's ordinary equivariant G theory is same as ordinary G theory for any unipotent group. Unipotent group has no non-trivial equivariant K theory, same as ordinary K theory. For ordinary G theory, actually not K theory, that is because of homotopy invariance. So again, so then this becomes isomorphism because of the homotopy invariance. And now comes the fact. But now you see, if you recall, what is GB? GB is a flag variety, right? But so it's a projective, in particular it's projective, then you have a push forward, right? And it's a smooth. So it's a push forward to Gg of x times Rg, here it should be G naught. G naught, G of point, right? But what is this? So this is same as G of x tensor Rg, and this is Rg itself. What is this? This is same as G of x, right? So you see, what did we do? We started with Gg of x here, right? And we ended with Gg of x again. So you have this map here. And the point of this map is identity. It's not difficult to show at all. So what did you conclude? We started with Gg of x, went to Gt of x. From Gt of x, I came to Gg of x. There is a projection, that this composition is identity. Right? So in particular, the conclusion is that Gg of x is a retract of Gt of x. And in fact, the point is that this is nothing but gt of x in while group invariant. If the this is not quite true, but this is true in this is first statement is always true, but this is true with some mild condition, namely what is called that there is something called the torsion index of the group. The torsion index is 1 or something, which means that you take a reductive group where those reductive group for which every étal locally trivial G torsion is also Jansky locally G torsion. I mean that the torsion index is 1. So, for example, for GLN, SLN, and so on, this does happen. Right. So, and it's very good because forget about this equality, but this itself is very important. This tells you that if you can prove any theorem about this, if you know this, then you know about this also. Because this is a retractor. This anything you can prove for here, you can prove for here. But now this is T, it's a split torus. And this is very easy to understand because the representation theory of T is very simple. So as a consequence, if you are working with a linear algebraic group, if you remember, if you have a linear algebraic group G which is not reductive, then particularly if you have characteristic 0, this has what you call the Levy subgroup. Such that if you take G mod L, then you get this reductive. So you can always reduce to the its reductive quotient, or which is a subgroup also. So that is L times reductive is the semi-direct, G is the semi-direct product of these two. And since L is the Levy subgroup, so basically it has no non-trivial algebraic K theory again by homotopy invariance. So you can always reduce to reductive. So the consequence of all these reductions is that the equivariant K theory of linear algebraic groups can be always reduced to understanding the equivariant K theory for torus. That's why torus action is very important to understand. Everything can be reduced to this. That's the one of the main thing I wanted to kind of explain, that why the study of torus equivariant K theory is very useful. Right. Now let's go to that. So, okay, so in this theorem, what did we use actually? Only thing we use is the Morita isomorphism, which I want to explain in more details now. So here is Morita. This is very useful again, Morita equivalence. Very useful fact in equivariant geometry actually. Not only in K theory, but any equivariant geometry. So it says the following. Setup is that you have H is a closed subgroup of G, and X is not a G scheme, but it's H scheme. Now everybody knows I can do induction, right? So I can define Y equal to X cross G over H. Right? Where H X on G by usual multiplication and H X on X. And because H X on G is 3, so you can check that then this H X on product is also 3. So I can take the quotient, and if X is quasi-projective, this quotient always exists actually. And which is our Y. Right. So you have a functor from H scheme to G scheme. Right? And this functor is called Morita functor for us. Many people say induction also, but it's actually induction, but I call it Morita functor. So what is the property of this functor? Well, so now let's go to this. Let me explain this Morita a little bit. What it does. So okay, so here it is. So now you see that here you have X. This Morita thing is very interesting. So this is G, and they have projection from X cross G to G, right? X cross G to X. Right, it's a projection to x. So, and the point is that, so remember that, so since you have taken x cross g modulo h, I can take this also. And this is my, now I am taking a stack quotient. I think now I am first time using a stack. I was trying to avoid, but now I cannot. So this is a quotient stack. If somebody knows stack theory, then this is a quotient stack. Life becomes much easier. Right. Because remember, we have already gone modulo h here. So this you can also write as x cross g mod h, a stack quotient. And this is the projection. Right. Now, what you can say about this map? Actually, it's very easy to show if you know algebraic geometry. This map of a stack is a G torsion. That means that it all locally on this stack x, it looks like x cross s, the quotient stack times g. In particular, in particular, what happens is that, so remember this was my y, right? This was my y. In particular, so you have this y and you have this x mod h. Oh, what I'm writing. X mod h is a stack quotient. For this, I call this PR. Because this is a G torsion, if I take, it just means that if I take the stack quotient by G, then this becomes iso. Right? So this is a fantastic thing. So what it says, if you understand this, it says that understanding the equivariant H equivariant geometry of X is same as understanding the G equivariant geometry of Y. For example, let's take G any linear algebraic group, which means that by definition there is a closed embedding into GLN. Right? So I could take this to be H and this to be G. Then it says that you want to understand the equivariant geometry of X, which X is a G scheme. Then actually this is same as I can go to Y and then I can go modulo GLN. In other words, and then now you see that because GLN is basically is like a special group. A special means its torsion index is 1. That means that for this is true. That it's K theory and most of the geometry is same as you take Y mod T, this stack, and take any cohomology theory and take its Weyl group invariant. Right? So see where I am going. So well, so I started with X, which is a G scheme. Now I don't understand this G. This G can be very, very complicated, right? Some very arbitrary reductive group. But I understand GLN. It's a special group, and I understand torus. I want to go back to my GLN. So I use the Morita here. So I go here, and this is just a property of a special group because GLN being a spacer. So you see that the conclusion is that anything you want to know about equivariant geometry of X for xn of G, you can always reduce to understanding equivariant geometry of Y for Tx. And remember here we have shown some theorems that these two are strongly related, right? We saw some theorems that if you know this and base change to T, you get this, or you can, if you know this, you take the while group invariant, you go here. So the conclusion is that again, using this, the Morita tells you that you can always reduce every equivariant K theory to equivariant T theory. And that is what we used here also in this theorem, namely this Morita here, right here. Okay, so right. So this kind of theorems are very useful. This Morita theorem is very useful if you are studying either representation theory or you are studying any equivariant cohomology theory, either algebraic or topological is very useful. Right, and actually, this Morita theorem, I don't know whether this word is used, but if you see the papers of Atiyah and Ziegel and Atiyah-Ziegel completion theorems and stuff like that, this Morita is very strongly and very heavily used. Right. So now, what do I want to say? So I have very few minutes left, so I should quickly wrap up. So I should, in the end, what do I tell you? Some more application of this. So now finally, yeah. And another thing, remember that I did not tell you that I should remind you that remember that we have this spectral sequence, right? This spectral sequence, right? So in particular, here if you take, suppose you take H to be trivial, then you get a spectral sequence E2PQ equal to tau over RG P. This is Z, right? And this is uh, G GQ of X. And this converges to just ordinary K theory of X. In particular, if X is smooth when G theory is same as K theory, then it tells you that there is a very close relation between equivariant K theory and ordinary K theory. In particular, if you apply for P plus Q equal to 0, you get that K naught of G of X tensor Rg over Z, then this is actually isomorphic to ordinary K theory of X. And again, this is very, very useful theorem. So, why I am mentioning this is because you see that you may ask, at least particularly for me, why one should study equivariant K theory or any equivariant cohomology theory. So my interest is not just to compute equivariant K group. I am interested in computing ordinary K theory. How do I do that? Because I come from K theory and algebraic cycles and algebraic geometry. I want to study K theory of X. And I want to particularly study K theory of those varieties which are some group actions. There are many, right? Like projective space. And you take all flag varieties, toric varieties, they are always equipped with group action. How do you compute some cohomology theory for such groups, such varieties? And the theorem is this theorem actually. This is the key theorem actually. This is very, very useful. Why? Because it tells you that, in particular, see that if Rg is, if G, remember G has some finite resolution as a projective Rg modules. So using that resolution, you can, and tensoring with G, this you can compute this ordinary K theory. And as I told you, that if suppose G is simple, nice enough, like reductive or torus, this equivariant K theory is very easy to compute. Very easy mean in the very loose sense, but of course, I mean, it's not very easy in the sense that you can just compute it, but much easier than this. But then this theorem tells you that you can always compute ordinary cohomology theory of a group variety in terms of equivariant cohomology theory. So it's like, it's very strange. It's not that you can compute equivariant cohomology using ordinary cohomology. That is, that you can do that, but that is not straightforward. That goes through something called the Atiyah-Jigel completion theorem. But that's not very nice, because you have to lose a lot of information. But here we don't lose any information. Actually, you can, on the node you can compute ordinary K theory or any ordinary cohomology. This holds for any ordinary cohomology. You can compute it in terms of equivariant cohomology theorem. And that's why this theorem, already for H equal to trivial group, this spectral sequence is very, very useful. So this allows you to compute, once you know this, you easily know this, just by tensoring with Z. Right. These theories are very useful because they allow you to often compute ordinary cohomology groups. Right. Finally, I should just, here I am. And right. Then what happens? Then remember that we have a natural functor, right? From G equivariant algebraic vector bundles on X to G analytic equivariant topological vector bundles, complex vector bundle, topological vector bundles on X analytic. Right? So clearly you get a map from Kg of X to Kg topological of X analytic. So left hand side is algebraic K theory of scheme X, and right hand side is topological K theory of this complex manifold Xn. What's the relation? Well, in general, this relation is not really very nice. Of course, you cannot expect this to be very nice, because you may have lots and lots of topological vector bundles which cannot be algebraic. Right? You cannot give algebraic structure on that. That itself is a very big problem, that when a topological vector bundle becomes algebraic. So you cannot expect that. But sometimes you may expect injectivity though. Well, maybe this is a faithful kind of functor, but not, definitely cannot be full. So, well, so actually it's not really, yeah. So let me just say anyway. So what you can say? So if you take with integral coefficients, you cannot say much actually. The relation is pretty bad. However, suppose you take with finite coefficients, let's say mod n of x. This is, what is this? This, you take this S1 spectrum and smash with the mood spectrum for given any n, you can smash, you can define something called the mood spectrum from S1. And smash with that mood spectrum is called the mod n algebraic K theory. Similarly, you can do here. Now call this map theta. Now there is a conjecture. This is a conjecture called Cullen-Lichtenbaum conjecture. Which says that suppose that dimension, this is dimension as algebraic variety is D. Then the Cullen-Lichtenbaum conjecture predicts that theta, let's call it theta, let's call it theta I from K G mod n I of x to K G top mod n I of x analytic is injective for I bigger than equal to D minus 2 and iso for I bigger than or equal to p minus 1. So it's not so bad. Furthermore, as you see that if you take this kg mod n of x, remember this has a bot element, right? So you can invert bot element, which I don't have time to explain, but it's not difficult to explain this. And one knows that in topological K theory, bot element is already inverted. So you get this map induces this map, and the theorem is that this map is a weak equivalence. Right. So well, I mean, you have to be careful that I should say that some maybe after some completion, some archaeological completion. So, but this is not so good because you have to do a lot of things. You have to bot invert, do some completions. But Cullen-Lichtenbaum is very straightforward. It says that this map should have this property, and the theorem is that Cullen-Lichtenbaum conjecture is true in most of the cases. I should tell you here that should be not G analytic actually, but you should remove this and you should write here M. What is M? M is the maximum compact subgroup of this Lie group G analytic. Remember that if you take the maximal compact group of a Lie group, complex Lie group, then this is a homotopy equivalence. So the equivariant K theory is not going to change. So you usually work with the compact groups when you are studying equivariant K theory in topology, and this relation holds. And Cullen-Lichtenbaum clearly tells you like when this map should be iso. So if you take I sufficiently big enough, then there is no relation, no difference between algebraic K theory and topological K theory. And that's a remarkable fact actually. Why? Because it's not topological K theory is easier to compute, so you can go back and compute algebraic K theory. So I think I should stop here now. So I should thank again.
Thank you, Professor, for this wonderful lecture. Does anyone from the audience have a question? If not, then we can thank the speaker again and close the session.
Should I stop sharing the screen now, Maynard?
Yes, you can.
Okay. So should I close it now? Really?
Yeah.
Yeah, okay. Thank you.
Thank you very much for the lecture. By the way, can you share me the notes?
Share notes with you?
Yeah, over the email. The one that you have. The one
email,
that
right?
Yeah.
Yeah, I will do that.
Yeah. Okay.
But
Thank you
I
very
will
much.
not be able to do it immediately because I am traveling in next few days. But as soon as I have time, I will try to do it.
Yeah, do it at your
And
convenience.
in case I have not done it because I forget things very quickly, just remind me.
Yeah, sure. Okay.
Yeah. Okay. Thank you.
Bye-bye.
Yeah. Bye.